Okay, welcome back. We're on page 107 talking about the merge sort. So here's what the merge sort basically is. We take the middle, right? In other words, whatever the size of the array is split it in half. And then we sort the little half and we sort the middle half, the first half and the second half. And then we merge them together, right? So I take a list, I cut it in half, I sort this guy, I sort this guy, and then I put them back together. Okay? Isn't that pretty cool? Because merging the list is actually a pretty simple thing to do. Now the thing is, let's talk about the merge sort and merge list guy. Okay? So one of these guys is going to have to be recursive. So it's going to be the sort guy, it's going to be the one, and then the merge list guy is going to happen. So let's take a peek at, this is how that part works. This is just like, I don't know, not really overhead, but the starting procedure. Yeah, it starts. And then what the actual merge list is supposed to look like. So I start off with, figuring out, I have, a start one and an end one, and a start two and an end two, because remember I got two lists, right? And so I'm basically going to go through and say, hey, is the start one and the start one? If this one is bigger than that one, well then the resulting one goes here. If this one's bigger than that one, then the resulting one goes there. So it's just basically a loop that goes through and says, hey, put all these things, either steal it from, in other words, the result either comes from the one list or the two list, whichever one, and go through. And then, fix up the result, and then fix up the result, and then the final one, makes the thing so that everything is perfect and the list gets put back. So this has some space complexity issues because the resulting guy kind of gets in the way. We have to build an extra thing, and then you have to copy the resulting array back to the original array and then start over again. So a tiny bit of space complexity. Okay, so this is where things happen. This start to end kind of guy, right? That's kind of where things start to happen. Okay, so let's talk about this guy. So obviously the merge is where the actual action is, right? That's where things get moved around. That's where work gets done, okay? Now, you might think, well, work gets done here. Nah, not really. I mean, all I'm doing here is just splitting up things and passing things around. Merge list is where things actually take place. That's where this element gets put into this pot. That's work. So when it comes time to instrumenting this thing, you're going to have to instrument inside these guys. Now, you could say, well, maybe inside the while loop is sufficient, because that's just going to tell me how to build the guy. Kind of, sort of. And then, so if they're smaller, if they're not, I'll just take them all from N1. If they're not, I'll take them all from N2. So somewhere inside here, I need to have like a loop counter. I might want to have a loop counter at the while here, maybe inside this guy. Maybe it's just an if statement, but so I don't know, So maybe one there, and then one in there, and one in there. Maybe after you've done a little experimentation, you might declare that these little for loops where I'm pulling them all from list 1 or pulling them all from list 2 sequentially aren't really that significant. Maybe. I don't know. You're going to have to figure it out. Okay. So, the worst case in this is everyone has to move everyone every single time. Okay, as it turns out, the best case and worst case scenario are essentially the same again. So once again, because the best case and the worst case are going to be identical, there's no need for me to do any calculations whatsoever to calculate the average, because I already know what it is. If they're both n times log n, then that's going to be the average too. Does that make sense? Okay. So moving along. On page 113, they start talking about the quick sort. So the quick sort is yet another recursive guy. All right, makes sense. It calls itself. It's kind of sort of similar to the selection thing. Remember the selection guy we did back in Chapter 3, where I'm trying to find out what the third largest, right? I don't want to know like what the largest is necessarily. I want to know the third largest. So it's kind of similar to that. What you do is you pick a value. It's called a pivot. You pick a pivot point, and then you break the list into two pieces, and then you evaluate this list and that list. Kind of sort of similar in concept to what we just did with the merge guy, but it's somewhat different. So yes, you do call it a pivot, and the pivot is all the things that are smaller and all the things that are larger. So here's how it looks. So I got my first element, and then I pick a pivot point, and so some of the things are below the pivot, some of the things are beyond the pivots, and then some of them I haven't got that far yet. So this is unknown, and then the last. So the first element, the last element, how far I've gotten so far, and then which ones are below and which ones are above. Okay? So the pivot just breaks it up into smaller chunks. That's all it does. Okay, so the algorithm has two parts to it, kind of sort of similar to what we just did. It looks kind of sort of similar, doesn't it? Where I do a pivot list, where I break this thing up into a list with the first, the list, the first and the last, and then I do a quick sort on the back half and the quick sort on the other half. Okay, kind of sort of makes sense. Let's go look at the real algorithm for doing work. And here's that part where I just go to the last element and figuring out, hey, if it's less than that, I move it around. If not, I swap. And then move the pivot to its location. After you've consumed the pivot, you have to move the pivot. And then you return pivot point and keep going. So once again, this one, you probably need to look at the stuff in supplemental materials to make some sense of this. Okay. So this part, the index, is equal to first plus 1 to last. That's probably the key to it right there, this guy right there. The swap is where actual work gets done, because you remember, pushing numbers around and counting and listing and doesn't actually do anything. This is what actually does work, is the swap. So it looks fair to obvious to me of where I would instrument this. I'm instrumenting it where work actually takes place. Okay, just saying. This is very similar to the thing we had about in the insertion sort. I put a counter here, and I put a counter there, and then I ended up putting a counter at, so cool. That's what this is all about. Okay, the worst case scenario for this guy is in squared. So it's not fantastic. Worst case. It has to do an awful lot of pivot moving to be able to pull that off. But the average case is back to this guy. So all the ones we've done since the very beginning, too, have had the same average big O notation. Does that mean they're going to be equally well? Not necessarily. It just means they behaved roughly the same when it comes time to increasing the size of end. It does not mean that they're always faster or always slower. Okay, that's not what it means, because input classes can make lots of differences, and there's some cool little tricks that we're going to have to learn here in just a moment. Okay, on page 121, they talk about the external polyphase merge sort. So it's a merge sort, except what happens if you got something that's just so dang big that it can't possibly fit in memory. So your tiny little device just doesn't have enough memory to hold it all. So you have to do sorts of small things and store them off to a file. Then sort and store them off, just like the merge guy did. Okay? And you just write them off as files, and then you start pulling up files and combining and compiling, and just keep going and going and going. Now, this is not incredibly efficient, because it takes all the time in the world to store things off to disk and then work on another smaller chunk. So can you imagine a list where you work on, the first 10, the second 10, this, and then later on you combine this guy and this guy and this guy, and it's sort of like a tournament method when you actually end up at the end with all of them sorted. So we're not actually going to do one, but you need to know why it exists, what's it for, not necessarily how to do it, but yeah, you kind of need to know what it's for. Okay, So let's talk about, and now that we've done all of the 7 sort routines that we need to do, let's talk in general terms. So first of all, how do you classify sorts? Well, one way to classify sorts is whether or not it's a stable sort or not. Now, I'll confess, when sorting integers, like we're doing in our assignments, stable or unstable has no effect whatsoever, because the first 14 in the list and the second 14 in the list are not at all unique, and I don't need to know that this one was the one on the top. Okay, I don't need to know that. Other scenarios, that's not necessarily the case. I mentioned the example of the sorting on an index. I need to have a stable sort for that. But anyway, so one way to classify is whether or not it does a stable or unstable. Another way to classify them is whether or not they're recursive or not. Okay, because there's going to be some space complexity issues with whether or not it's recursive. That kind of sort of makes sense. Okay, and then some other ones are just talk about the shape of the curve, right? So obviously I want n times log n, right? That'd be a good thing to have. So let's just go through them. So the insertion sort. The insertion sort is actually pretty doggone efficient if n is not very big. So if you have a small array, insertion sort probably is a good choice. Okay? Just saying. Bubble sort, probably never. Okay? I can't imagine you would use the bubble sort for anything at all. I'm just saying. It's just not something that we would normally use in a production environment. Shell sort. I would use a shell sort when memory was at a premium, or I need to move things around, but I don't want to have any space complexity kind of issues whatsoever. Okay, that'd be a good one for doing shell sort. Okay. Radix sort. Now, radix sort is relatively efficient, although it has some huge space complexity issues, which almost always disqualifies it. But remember, if the log of the size is greater than the number of digits, then there's an optimum point. When this thing is tall and skinny, you're good. If it's short and wide, it's not good. Looking at the height and the width, it's very predictable. The radix sort. In other words, I can tell you exactly how long it's going to take. Now, let's talk about that. So the heap sort and the radix sort are both very predictable. And you might think, well, what do I care if it's predictable or not? Okay, here's a crazy scenario. Let's say, I don't know, you're doing a missile defense system, and you're shooting a missile to take out another missile, and so this thing fires off into four warheads. And so your job is to prioritize the threats and take out the missiles, okay? But these things are moving at very, very high speeds, and I only have like 21 milliseconds to make this decision. So I need to sort the threat, but I need to know exactly. This thing can be done within 21 milliseconds, absolutely, positively, no exceptions. See how sometimes you absolutely, positively need to have the shortest amount of time to be able to get. In other words, it has to be done within so many milliseconds, or things are going to go bad. So yeah, in an industrial operation, having a predictable sort time is probably a good thing. Hey, we're coming up on the 15-minute mark, but we'll finish this in just a few.